In this chapter, we look at the governing equations of fluid mechanics. So that would be chapter 2. And you will see that every year, the first question of the exam has one part on the derivation of the governing equations. The full governing equations are called Navier-Stokes equations for fluid dynamics, and they are a little bit lengthy to derive from first principle. So instead, what I will do during the lectures is demonstrate the principle of derivation by looking at one of the simpler form of equation, and then explain the full derivation in context, and then make sure that you know how to derive this equation from first principle for simple cases. That is, cases where you may neglect, for example, viscosity or velocity gradient in one direction or another. And essentially, that's what you are expected to be able to do during an exam. Okay, so first exam question will have one part, approximately 10 points out of 25, which will concern this, what we're going to do this week. Right, so you should open your overhead documents, chapter 2 or overhead 2, and we'll proceed now. Okay, so the next slide here just essentially talks about what it is that you're looking for when you're solving a fluid flow problem. If it's just fluid interaction with a structure, and what I mean by that, for example, wind blowing around a car, wind blowing around a house, and you want to know the pressure or the force experienced by the house, or simply the effect of the house on the fluid, because it may induce a mixing of pollutants, for example, in your urban area or anything like that. Okay, so what you're trying to solve in that case is just pressure. Your pressure is a thermodynamic quantity. And you also need to know the velocity everywhere in time and space. And that's the case for both. So how would you describe mathematically those two quantities? Pressure is a scalar because it's defined just as a quantity with magnitude only. Okay, so essentially it has a value which may vary depending on the problem with time and space in 3 dimensions or 2 dimensions if you can make certain simplifications. The velocity, the flow velocity, that is the speed at which it moves, is not a scalar anymore because, well, the speed is, but if you're interested in the velocity, you're interested not only in the magnitude of the speed, but also the direction of that displacement. So when you combine speed, which is the magnitude of the velocity, with direction, you get what we call a vector. And that vector, if you express it in 3 dimensions, can be written in the Cartesian coordinate system in terms of its component, u, v, and w. These letters are traditionally used in fluid mechanics to describe the components of a velocity vector in the Cartesian coordinate system. Each one of these, u, v, and w, is a function of time and space, and each one may be a different function of time and space. That is, they vary differently with time space. So what we're trying to solve in fluid mechanics is essentially these two quantities when you're not interested in other things such as temperature. And that means finding their value everywhere in time and space, which is a huge challenge because in fluid mechanics, things vary very quickly. Even over a micrometer space, you can have a bit of a difference in the velocity or the gradients and so on. Okay, so we definitely need that, and then generally it's dependent. These solutions are dependent on the fluid properties, for example, just to name 2, density and viscosity, which we discussed at length. To solve it at every point in time and space usually means finding what we call an analytical solution. That is a solution which is defined mathematically as a mathematical function of time and space, that is a function of t, x, y, and z, for example. That is only possible in fluid mechanics with very simple test cases, and you would have looked at one in second year. Only a very simple one. So practically it is of limited use when it comes to practical engineering. Okay, so you have alternatives. You can use 2 equations that are derived from series of experiments that are there to allow you to make practical engineering estimates of quantities of interest. For example, the force experienced by an object exposed to a fluid flow. Okay, the other tool that's available now and it's growing in importance is computational fluid dynamics. That is a computational tool to allow you estimate values for rho and u. And the first step in a computational analysis is to decompose space into continuously spread discrete volumes. When you put them all together next to each other, you don't create any void. They continuously fill space. And these control volumes are generally in computational fluid dynamics called cells, mesh cells. The combination of all the cells is called a mesh. It's essentially the discretization of space. In fluid mechanics, there is a method of solving for the governing equations using what we call the control volume analysis or control volume analysis approach, which means we solve the governing equations on average over the control volume. And that's the foundation of control or computational fluid dynamics. Very often we start from control volume analysis. We talked about it in second year, and we'll revisit that now because it's the easiest way to explain how the governing equations of fluid mechanics are derived. So essentially you have to think of, you pick a small volume in space anywhere. For example, this cube, using a cube is convenient because it means the faces are aligned with the coordinate system axis, X, Y, and Z direction. So you pick a cube, you've got a point at the center of that cube, and you can see how the flow variables change over that cube in order to derive from first principle the governing equations. Let's go to the next slide. These governing equations, called the Navier-Stokes equations, as seen here, appear reasonably complex at first sight. And these are only for what we call incompressible flows, so certain simplification where possible. We assume constant flow properties, that is the densities outside of the derivatives. So is the dynamic viscosity. You've got the density here. These are the components of the acceleration of gravity vector, gx and gy, the component in the x and y direction. You recognize pressure, velocity in the x direction, velocity in the y direction is v. So essentially what I need to do now is show to you how they are derived, and we'll start with the mass conservation. So they are derived essentially from physical principle of all physical processes, or I suppose a principle of mass conservation. And from that simple principle, starting from a control volume, you get an equation like this one. So what's that process? How do you get there is what we'll do. But before, let's look at what they would look if you were in 3 dimensions, so real space. You simply add a third dimension here and a third equation for momentum conservation. We'll start with mass conservation because it's a lot easier to work with. So what's the mass conservation principle? If you think of a control volume, which is in 2 dimensions, because we'll look at 2-dimensional flow. 2 dimensions, by the way, means that the flow variables only vary in 2 dimensions, that is in a plane or in a surface. For example, the plane of the slide here. And we assume that variations in the direction perpendicular to the slide are negligible. We don't account for them because things are the same no matter where you position yourself in the direction perpendicular to this. So the principle of mass conservation is written here in mathematical form. So what does that mean? This is the sigma Greek letter, capital letter. It's used as a symbol to mean discrete summation. Discrete means you have a finite number of different variables that are summed, and the different variables are all written with an M and a dot on top and an increment I. So the increment goes from 1 to capital N in. N in stands for the number of inlets to a control volume. So we sum this quantity over all the inlets that may exist. This quantity is called the mass flow rate. That is how much mass flows through a surface per unit time. The units of it would be kilogram per second in the international system of units. Okay, so we have the mass flow rate going into the system minus the mass flow rate going out. And we assume that these quantity m dot and m dot are all positive, provided that we correctly assume this was an outlet and this is an inlet. So essentially we're saying if you sum all the positive mass flow into and you subtract all the positive mass flow out, if they balance exactly each other, then you end up with a 0. And then the left-hand side tells us what is the time rate of change of density times volume. So that would be the density of the fluid inside a control volume. If you multiply density by volume, you get the mass inside the control volume. So V here is the volume of the control volume. So the volume of that square. So if you multiply density by volume, density of the fluid in there by the volume of this, you get the mass inside. And this tells us how does the mass inside the control volume change with time? Well, it changes only if you have an imbalance in the flow going in minus the flow going out. If you have more going in than out, this quantity will be positive, and that means the time rate of change of mass will be positive. It means mass increases. You pack more fluid inside the control volume than you take out. So that's the expression, the mathematical expression of the principle of mass conservation. Okay, so it's the very beginning of your derivations. Okay, so then we have a busy slide here, and perhaps before I go into that, it'd be worthwhile just going back over some basic principle from second year on mathematical expressions. So I will call this, okay. If we have, I just went through that early on, I want to go back and define what a mass flow rate is. Okay, so the mass flow rate is written m dot, and we have a mathematical formula to define it. This stands for surface integral over the control surface. So CV stands for control volume, CS stands for control surface. Well, let's take any surface. Okay, if you multiply the density by the velocity vector and by the area vector, and I need to define that area vector over the surface. Where does that come from? If you have any surface, let's say something like this, let's break it down into discrete surface. Okay. And you've got, so that's an imaginary surface in 2 dimensions through the domain. Okay, you've got your imaginary surface. The fluid comes, let's say, from the left, and it's going to come in like this. So it's somehow moving upwards. I stopped the line here because I want to draw vectors after that. But essentially, it actually goes through the surface. I'm just going to assume it goes in something like that. Okay, just completely arbitrary. That doesn't really, it would mean that essentially the fluid goes in like this, then it's deflected like that. Perhaps we put another one, goes in, and inside. So of each one of these, let's zoom in on that particular surface there. So we've got something like that, which we can simplify as a straight line. And the dot represents the center. It's not really at the center here or here, but it's supposed to be at the center between the 2 points. Okay, so I drew it more at the center on the right-hand side there. So at the center, we know the fluid moves with a velocity like this one. So that's the velocity of the fluid. Remember, it's a vector. And that's a discrete area. Let's call it AF, the area of that small surface. The surface has what we call a unit outward normal vector. Unit because the magnitude of that vector is 1. And the property of that unit outward normal is that it is perpendicular to the area and the surface of area AF. If you want to know how much fluid is going into this surface, on the surface that's between here and here, that is between here and here, you need to project or decompose that velocity vector into 2 components. This one, we'll call it the tangential component. This one is the normal component. Okay. The way you get that normal component, why do we need to decomposition? Because the fluid effectively has, if it has 2 vector components, means it moves in a component parallel to the surface and perpendicular. The fluid that slides along the surface doesn't get into the surface, so it doesn't contribute to mass flow through the surface, I should say. Okay, so this component here does not contribute to mass flow through the surface. The only one that contributes to it is the normal component. So if we were to write that mass flow rate through that surface, we could write it as the magnitude of the normal component multiplied by the area and multiplied by the density. Okay, so here, if you were to multiply Vn by AF, you would get units of meter cube per second, and you multiply by kilogram per meter cube from density, you get units of m dot is kilogram per second. Okay, now what we've done here in using that formula is we've assumed that Vn was constant, or uniform, I should say, uniform over AF, and rho as well. Both of these are uniform over the area or the surface over area AF. In that case, to get the volumetric flow rate, you just multiply the normal component by the area. So this is the quantity for volumetric flow rate. If you multiply by density, which is rho, then you get the mass flow rate. And we assume everything was constant. So clearly it is not constant here, there is a curvature. But in the limit, when you make that area very small, you will end up with all these constant or small enough to neglect the variations. And that transition from large to small enough comes from essentially the difference between discrete notation and integral notation. So this can be approximated, or in the summation over areas where n number of small surfaces used to discretize CS, where CS is this one. Okay, so basically discretizing means breaking it down into smaller areas, as we've done here. The smaller these areas are, the more surfaces you will get, the bigger n will be, but the smaller AF becomes. So this formula means summation. I'll drop the index there because it's we know it's there. Rho AF for each of the I, and then Vn for each of the I. And then eventually, you also have a definition for V, which I haven't written yet, or Vn. Where will I write it? It's getting busy. So Vn is equal to V multiplied by n multiplied by the area. Oh, sorry, the area is not there. Okay. So what's that scalar product? If you take that vector and you multiply it with a scalar product with this vector, you effectively project V onto the normal direction and you extract the magnitude of that projection. So this doesn't give you a vector, it gives you a scalar. The scalar product reduces the order of your tensor. You end up with a scalar, a quantity, which is the quantity or the magnitude of the components of V in the direction perpendicular. So we've got a simple formula. If we substitute that in the previous one, we end up with this. There's a scalar product there, which I know is gone missing, between the two, V and N. That scalar product gives you Vn, so this quantity is the same as this one. And if you look at what's on the right and what's on the left, you see the connection. Essentially, we now have defined that area vector. The area vector is okay. So for example, the discrete area I, this one. So if you multiply the area by the unit normal vector, so these two quantities multiply, you extend the length of Ni as in proportion to the area itself. So the area vector is a vector whose magnitude is the area and direction is the direction of the normal to the surface. So that's the explanation of this quantity. So it's a little bit long, but it's important, and it's useful to understand what we have on this slide here. So what are we calculating there? Rho u is effectively, and perhaps I'll use another slide there to show that, show the parallel between these two, and I'll come back to that slide. I'll sketch it very, very quickly and then switch to it. Okay, so we have our control volume in 2D. Okay, we have the volume itself, and we've got fluid coming in from the bottom left, let's say. So it means that when it intersects that surface, it will have a certain velocity like this one. It may have a velocity like this one here, this one, this one. What you want is just to extract the normal components. So if we call it the outward normal components, it points out of the control volume. So if we just focus on this one here, or I should perhaps, let's start with this one. This one would be the projection of the velocity vector down. If this is v, and we have our coordinate system like this one, where we align the faces of our control volume with the axis of the Cartesian coordinate system, the component will be u. Okay. So we just take the x component of the velocity vector, and that u will be effectively minus, the minus doesn't come up that well, minus v scalar product n, right? Why minus? Because the vector is going in the opposite direction. The velocity vector v here is going in the opposite direction to the outward normal. Outward means it points out of the control volume. So if we take a scalar product of these two, it will give you a negative value because they point in the opposite direction. If you want just the velocity component x, you see v points in the positive x. Here points in the positive x as well. Okay, so you know how to extract Vn. So if we want the mass flow rate through this face on the left-hand side, if it's positive in this way, we end up with the mass flow rate would be equal to, remember the previous formula, it's the density multiplied by the normal component, u, which is positive, multiplied by the area itself, or the area of that face. We wrote it AF previously. So that would be, if we want a positive u, then that would be minus rho. That's it. Okay, different ways of writing it. But we know that v dot n is negative, so we put a minus in front to get a positive. So that u is positive in this case. So how do we compare that with our previous slide? This is what we had here. Just rho u, okay? So that's not the mass flow rate. It's actually the mass flow rate divided by the area of that face. So instead of writing area AF, we wrote it AW, meaning the west face of our control volume. This is the east, this is the north, and this is the south. So M dot W means the mass flow rate through the west face divided by the area. It gives you essentially a mass flow rate per unit surface area flux. So you end up with, we know what rho u is. It's the normal component of the velocity, and I should have a minus there if I'm consistent with my previous notation. But what we're going to say now to make it simpler is that I'm only writing the positive value. So assume Vn is positive. Everything here is assumed positive, and it will make sense when we look at the rest. So that's just to simplify. These are just positive quantities. So rho u here is the amount of mass that flows in per unit area. If we know the value here, then we can say, let's use calculus to find a formula for the value of flux through this phase. It's going to be rho u plus a change, which can be negative or positive. So it's rho u plus the rate of change of rho u as you move along the x direction, multiplied by the displacement along the x direction as you went from there to there. Okay, so if you look at this, take the rate of change multiplied by the change, the delta x cancel out, and you get your rho u plus the change in rho u, d rho u. You do the same for the bottom. So we extract the normal component to the face for the velocity, which is the y component of the velocity vector, right, and v rather than u, and we do the same for the change. Okay. So that's what's explained here. We changed by delta x, and therefore we got that change. Let's go and look at what we had as a principle of mass conservation. The total amount of mass into, and we took the positive mass flow rate, total amount of mass going out. So let's go back to the sketches from the previous one. What goes in if rho u is positive is this and this. So they both go into the control volume through the face, and these go out through the control volume. Okay, so it's based on the sign of the arrow that we make that assumption, and the sign is correct provided that this is positive. If this is negative, then the sign is the opposite. So we'll talk about that distinction afterwards. But these are the two inflow, and you see here that should be the inflow. So the two inflows are written here, rho v, rho u. But if we want the mass flow, we need to multiply that by the area of that face. Remember, this is the mass flow per unit area. So the area of this face is the height of the control volume. And because it's two-dimensional, we assume that the length or the size of that area in the direction perpendicular to the screen is 1. Okay, two-dimensional, dimensions in the z direction are assumed to be equal to 1, all of them. So the area of that face is delta x multiplied by 1, it's delta x. So that's what we have here, rho v and rho u. Sorry, rho u, did I say delta x? Sorry, I meant delta y here. The height is delta y, it's the distance in the y direction. So rho u multiplied by y is the mass flow rate through that face, and rho v multiplied by delta x is the mass flow rate through that face. That's what we have there and there. You do the same for the north and east. So the mass flow rate through that face is all this, multiplied by the area, which is delta x. And the mass flow rate through this one is all this, multiplied by delta y. We have them now. So all of this is what we've written right here. If you look at this minus rho u times delta y, you see, the rho v minus rho v times delta x, the rho v and the rho v times delta x cancel out. And you're just left with minus d rho v over dy multiplied by delta y times delta x. Just do the simplification yourself. For this and this, they cancel out, and you're just left with this one. So if you rewrite that, you end up with something with an error there. I'll need to correct it. There's a minus sign missing. Okay. So I'll have to update the loop site as well, but we have all these quantities equal to all that there. The left-hand side, sorry, is the time rate of change of the mass inside the control volume. Mass is density times volume. The volume is the volume of a square of depth 1 and width delta x and height delta y. So the volume is delta x times delta y. They are constants, but we put them here inside the derivation, but they can be taken out because they are constants. So if you take them out of the derivative and you make this equal to that, you end up with the delta x and delta y canceling out. Okay, so that's what we have here. And I see that the error has propagated, so I'm going to correct it here. I have minus, minus. This doesn't change and this doesn't change. I'll check the lecture notes as well for any error. So this is the equation of mass conservation, okay, where we divide throughout by delta x, delta y. The assumptions we've made is that you can say that this quantity is constant over the phase. That's true only for small phases. We've also assumed that the only variation in rho u happens in the x direction when we went from there to there. And then the same from there to there. They exist and we can build them in, but it turns out that their contribution, variations along the y, is balancing out because we calculate all that at the center of the control volume. And what happens when we divide throughout by delta x and delta y is we remove any information about the size of that control volume. Effectively, it means we assume it's a point. Okay, so and we neglect all the variations in a way that's consistent with our simplification, but it means that we end up with what we call a discrete or an equation valid at a point. Okay, whereas we started from consideration over volume, control volume analysis, and we moved to essentially satisfying the condition at the point, not anymore over the control volume. Right, you can then make further simplification. If your flow is steady, there is no time derivative. Okay, it means that things don't change with time, so this term goes to 0. And you're left with just that. The minus sign disappears because it's equal to minus 0, or your 0 is the same. If the density is constant over space, that is, perhaps it's incompressible, that this density doesn't vary with pressure and temperature or anything like that, or pressure, then you can say density is constant, therefore the time derivative is also constant. You can take the density out of the derivative and you end up with essentially the same equation. So this equation is mass conservation for an incompressible steady flow problem. It's valid, it has to be satisfied at every point in space. We derived it from first principle, that is this principle of mass conservation, by considering a finite volume in space, which we call the control volume of surface area, bounding surface area control surface. And if we go back to this derivation, we have it here, the one we just derived. I stop now for this video.